Hello, my name is Sean Aurora, and I have the honor of serving as the director of the Kendeda Building for Innovative Sustainable Design at the Georgia Institute of Technology in Atlanta, Georgia. The Kendeda Building is a 37,000 square foot indoor, plus another 10,000 square foot outdoor, multidisciplinary, non-departmental education building. It was designed and constructed to meet the Living Building Challenge, the world's most ambitious building performance standard. We owe a huge debt of gratitude to the various amazing green building standards that are in the marketplace. They have moved the market, building code, and conversation towards better buildings for the environment and occupants. But in a world facing environmental challenges and all of the social equity impacts that come with them, is it enough to do better? The Living Building Challenge asks, are better buildings perhaps less bad versions of the ones we currently have? If we could start with a blank slate, what would good look like? Friends, the Kendeda Building is what good looks like. It's a regenerative building that seeks to have positive environmental and social impacts. For example, it produces more on-site electricity each year than it consumes. It does this from renewable sources, and that reduces burden on the grid. It reduces stormwater runoff that would otherwise negatively impact downstream communities, and that's an equity win. During the construction, we diverted more waste from the landfill than we sent to the landfill. And why are we sending perfectly good reusable material to the landfill anyway? And what's most surprising to people is that the toilet waste is managed on site. That's right, our toilets don't connect to the sewer. And that's just the tip of this building's regenerative features. The Living Building Challenge looks to nature for inspiration on how to create regenerative buildings. And nature provides the perfect metaphor that encapsulates this regenerative ethos: a flower. Like a flower, a building should take everything it needs from its site. When the building is gone, it should leave more than it took. Flowers do this. They leave behind seeds. They leave behind more life. Therefore, the Living Building Challenge is framed around 7 performance areas called petals. They are place, water, energy, health and happiness, materials, equity, and beauty. And the requirements of all 7 petals have to be met to achieve full Living Building Challenge certification. That's why it's called a challenge. And it makes sense that all of the requirements have to be met. What happens to a flower if you start pulling the petals? The flower falls apart. So similarly, if a project team says, you know what, net positive energy, that's just too hard. Let's pull the energy pedal. Well, where does it stop? What's the next thing that gets cut because it's too difficult? That's why the Kendeda Building exists here, in Atlanta, in the South. Prior to the Kendeda Building, most fully certified living buildings were in the Pacific Northwest or the Northeast, parts of the world that have a substantially different climate than here in the South. As long as these regenerative buildings existed in other parts of the country, it was very easy for the naysayers to say, you know what, this regenerative building ethos, it works there. You can't do it here because, and you can just fill in the blanks for the reasons people came up with. The top reason, of course, was it's hot, it's humid. The best way to prove the naysayers wrong and take the it can't be done here argument off the table is by showing that it can be done. And then the conversation moves to, how do we get more of this done here? And that was the shared vision of Georgia Tech and the Kendeda Fund, an Atlanta-based philanthropic foundation that provided 100% of the design and construction costs of the Kendeda Building. We wanted a living building in the South that can serve as a catalyst for change, a model, a Southern solution for the unique environment we have here in the South. So with that introduction, let's talk about some of the specifics. All buildings begin with place, And to tell you more about the place pedal, I'm going to turn it over to my colleague, and I'm not making this up. His name is Steve Place.
Thanks, Sean. Just imagine, not long ago, this site was a parking lot. It's not unusual to see a building replace surface parking, but this building does so much more. It offers a template for regenerative ecology, which moves the site towards its pre-development characteristics. The project creates a microhabitat filled with native plants that support other native species. It manages rainfall much as a forest would. During a normal rain event, 90% of the water remains on site. Every aspect of this building is designed to slow the flow of water. The solar canopy and rooftop harvest approximately 40% of the site's annual rainfall and funnel it to a 50,000-gallon cistern in the basement. The building is surrounded with pervious surface and bioswales that allow the water to slowly seep into the ground.
Thanks, Steve. You might have picked up on this. Steve started talking about place, but very quickly included water. And that's because the performance areas of the Living Building Challenge are not silos. Going back to that metaphor, they're part of a flower, and therefore you really can't separate them. So we talked about rainfall. Now let's talk about another type of water, which is gray water. That's what's left over after you wash your hands and take a shower. In a conventional building, that gray water goes down the drain into the sewage system. In the Kendeda building, that gray water goes down the drain and ends up here, where natural systems, these plants and their roots, do the initial filtering of that gray water, and then we let nature take care of the rest. That is a natural solution, but this is also an amenity. As our students and our faculty and our visitors enter the building, this is what they're greeted by. We like to think it makes them happier. Speaking of happy, our bees who are on the rooftop, yes, we have rooftop bees here in the Kendeda building. We think this garden makes them happy because of the flowers. The flowers give the bees the pollen they need to make their honey. There's another type of water, and that's the water left over from the HVAC systems, the condensate. In a normal building, that condensate is typically just dumped. In our building, we collect that condensate water and use it to irrigate our landscape and our rooftop garden. And the last type of water is the icky stuff, and we'll get to that later. I thought I said we'd talk about this later. Well, because you're here, let's take a look at the most awesome toilets on campus. So what we have here is the talk of the town. There's a reason we say there's a lot of potty talk at the Kendeda building. It's because we should be talking about where our bio-waste goes. But before we talk about where our bio-waste goes, let's talk about the relationship between energy and water. I often tell people, if you want to make a local impact that helps address global climate change, go to the bathroom in the Kendeda building. I'll explain. Here is how fresh drinking water gets to a toilet. In our region, we start with a reservoir. That reservoir contains rainwater. Then we use electricity to pump that rainwater to a central plant that takes that rainwater and purifies it to drinking levels. We call that potable water. Then we take that potable water, use more electricity to pump that potable water to buildings like this one, where in commercial and educational buildings, the vast majority of that clean drinking water is flushed down the toilet. And then we've got this icky water, and that icky water has to be conveyed to a central wastewater treatment plant that uses more energy to bring that water to a level that's safe to discharge. That's our system. we have to step back and at least at a baseline accept we shouldn't be flushing drinking water down the toilet. Now, let me tell you how we do it here in the Kendeda building. We start with the same initial ingredient, rainfall, except we capture our rainfall on site, and then we bring it here to activate a foam flush toilet. And when you do your business here and leave, your business stays here. You're probably wondering how this all gets done, and I'm going to turn it over to my friend Stephen Ward, who is the facilities manager for South-Base Institute, a premier local environmental nonprofit. Stephen is perhaps the foremost expert on this system because South-Base has had a similar system for over a decade. So while you're talking to Steve, I'm just going to stay here and make some compost. Hey, listen, but before you go, take a look at this tile. In a normal renovation, this tile would have been thrown away. But what we did is we salvaged the tile and incorporated it into this mosaic. I'll explain to you why we salvage material later, but now just, why don't you go downstairs and I'll catch up with y'all. Thanks.
Thanks, Sean. It's a really cool system, and it's really broken down into 3 components. The first are the composting toilets. The second is the composter. And the third part is going to be the leachate tanks. So the first part, the toilets, are very unique in that there's no water sitting in the bowls. Instead, it is a mixture of biocompatible soap and 3 ounces of water per flush. The cool thing about that process in and of itself is that the most water efficient toilet out there uses 0.8 gallons of water per flush. So already these composting toilets use 97% less water than the most water efficient toilet, which is pretty cool. Not to mention, those toilets are also fed by harvested rainwater. So you're not even using any potable water in the process. So it's a mixture of the soap and the water in the bowls that help to lubricate the sides of the bowls, and that helps the solids go down, and they feed directly into this composter here. And so inside the composter is really where that magic happens. So in here we have a mix of nitrogen, of carbon, and of oxygen, and that balanced mix helps create this nice rich environment, almost like a forest floor, for earthworms and other organisms to convert that organic waste into reusable compost. The next part, or the third part of the process, is the leachate. So the leachate is any of the liquid that gets into the compost tank. And so the leachate will percolate through these solids in the composter, and that is then pumped out into the leachate tanks here and held. And that leachate is essentially a concentrated liquid fertilizer that Georgia Tech ships off-site to be reused. Or at South-Base, we use it in our front landscape, and it's distributed through a dedicated drip irrigation system. So it's a really awesome process, and the end result is even more awesome. But to top that off, it requires very little maintenance, although it does require some maintenance in order to ensure that you have a proper decomposition process. Isn't that an amazing process? Back to you, Sean.
Thanks, Stephen. I hope this has demystified composting toilets. A really simple way to think about it is we've brought an outhouse inside. Now let's go back to the benefits. At the beginning of this section, I talked about the global carbon benefits that result from using our toilets. The vast majority of electricity in the state of Georgia is generated by burning fossil fuels. So the conventional system has a lot of carbon pollution that's baked into it. And this system eliminates virtually all of that carbon pollution. So that's a global benefit. But what really excites people is the local benefits. Our region is a region that is growing fast, but our infrastructure cannot keep up. Every time we build a new building, that adds to the burden of the existing sewer systems. And these sewer systems are being overwhelmed. If we deployed more of this technology as we constructed new buildings, That would allow us to continue to grow without burdening infrastructure. The defining architectural feature of the Kendeda Building is our beautiful solar canopy. Therefore, it's not surprising that most people think that's how we get to net positive energy. But the first step of the process is not renewable energy. No matter where you are in the world, the first step is always energy efficiency. The more efficient you make a building, the less renewable energy you need to place on site. In other words, the less expensive it is for you to get to net energy positive. This building is 72% more efficient than a similar building constructed in this climate zone. And the way we get there is as follows. First, build it well. This building is so tight that very little air goes in or out unless we want it to. Therefore, the building maintains its temperature longer, and that means less heating and less cooling. Other things we've done is we've got triple pane windows. We've got the right amount of insulation. So these are things that help get the building as efficient as possible for what we call the envelope. That's the periphery of the building. Then there's the stuff that goes inside the building, the mechanical systems. You want to make those as energy efficient as possible as well. It's a very hot, humid, uncomfortable southern day outside. And in here, it's cool. But we're not using conventional air conditioning. When I tell people that this building is comfortable and there's no conventional air conditioning, people are amazed. They ask, how do we do it? And I say, well, we've got these big ass fans. And I can say that because that's the name of the company. But there's another thing. Underneath our feet, beneath this concrete, we've got pipes. In the summertime, we can run cold water through these pipes. In the wintertime, we can run hot water through these pipes. And we take advantage of the thermal properties of the concrete that slowly radiates that cool or warmth. And the advantage there is we only heat or cool up to here. We're not heating and cooling the void. So this combination of building well and then having very efficient systems allows us to put the minimal amount of solar that we need. In our region, that's the preferred renewable energy source. In other regions, it can be a combination of solar and wind, or solar, wind and hydro, or even wave. But here, it's solar. We have a 330 kilowatt solar array, which on average generates 450,000 kilowatt hours a year. And the building is going to consume about an average of 330,000 kilowatt hours a year. We're comfortably net positive. So in conclusion, with regards to energy, the basic ingredients are as follows. Build an efficient building. Place efficient systems, and then put the right amount of site-appropriate renewable energy to take you to net positive. Let's talk about materials. This used to be a tree that fell down on campus, and now it's a beautiful countertop. This ramp is made from wood that we salvaged from a deconstructed building. And these stair treads represent Georgia Tech's history and legacy. They come from the Georgia Tech Tower. In the 1880s, that's when that building was built. And this is original wood from the original construction. So think about it. The trees began their life in the early 1800s. And in a normal construction, this would have been thrown away. Why are we throwing away perfectly good material? Where is a way? It doesn't go to Mars, it stays here. And increasingly, it's having local and global impacts. So what we did is we salvaged that material and incorporated it into this building so this original piece of Georgia Tech's history can continue to inspire generations of Georgia Tech students. So the materials pedal has a very key requirement, which is that during the construction process, we have to salvage more material from the landfill than we send to the landfill. And the way we do that is through the incorporation of the salvaged materials that I just mentioned and more. You know, the salvaging of materials does incur labor costs. You have to have labor to deconstruct the building, to transport that material to a shop to get milled, and then to transport that finished milled product to the construction site. But here's the thing, that's local labor. If we scaled the incorporation of salvaged material into new construction and in renovations, we would spark a new industry that doesn't even exist, a salvage economy. So just think about it. Imagine going to your local home improvement store, the same way you go to your local grocery store, where you say, where's the natural food section? In your home improvement store, you'd say, where's the salvage material section? That's what's possible if we scale this to a regional level. There is so much contained in the materials pedal, I haven't had time to cover it. I haven't even told you about the red list. If you're curious about the red list and the other aspects of the materials pedal I haven't covered, please visit our website for more information. If there's one thing you remember from this tour, it's that if you've got so many things that you gotta do to satisfy a challenge, be thoughtful about how each thing you do can satisfy more than 1, 2, 3 requirements. That's what we had to do for the Kendeda building. Everything we did, we asked ourselves, how many of those requirements does it satisfy? Let me give an example. This ceiling satisfies 6 requirements of the Living Building Challenge. I'll count them down. 1, it's beautiful. At least we certainly think so. 2, did you know there's a technology that takes atmospheric carbon dioxide and it turns it into a building product? The technology is called a tree. And so we used a lot of wood because of its carbon benefits. 3, that wood was sourced from Alabama. That's because we have a requirement to source 50% of the materials used in this building from within 1,000 kilometers. Those trees were sustainably harvested. Then we also incorporated salvaged material from Atlanta's film industry that would have just been thrown away. And we didn't stop there. For those pieces that we didn't salvage, all the leftover material that would have normally been thrown away, we turned those into stairs on our ground floor. And we could have stopped there. We could have patted ourselves on the back and said, we satisfy 6 requirements of the Living Building Challenge. But here's the thing about the Living Building Challenge. Remember, it's a philosophy. You can't unlearn what you've learned. So we asked ourselves, is there something else we can do? And we realized there is. What does a building mean for local equity? So we partnered with a local nonprofit called Georgia Works. And Georgia Works has one goal: to help men at risk of chronic homelessness get off the street. And the way they do that is through shelter, education, nutrition, healthcare, and workforce development. 6 individuals from that program helped us construct this ceiling and went on to get marketable skills. We think that is one of the lasting legacies of this building and is a prime example of how you can think about doing more with one idea. So we've taken the challenge. Now, we challenge you to do the same. We challenge you to rethink what your expectations are of a building. Challenge your policymakers. Challenge the people who build your buildings to do more, to take us and this region to a regenerative future. Thank you very much.